Share screen. All righty, welcome everybody to our, is this the third mentorship session for our 2023 design competition? We are super excited to have you here. Just as a reminder, next week we're going to be going over performing a stiffness simulation. This one's going to be a really cool one. It's critical to the competition path. And Tyler Shaw, who is the VP of Engineering at PADT, he's going to be going over that. You'll remember from the prompt for the competition that one of the criteria that you'll actually be judged on is PADT. Tyler and his team will actually be doing stiffness simulations of your chassis. And that will be part of the grading criteria for the competition. So definitely a great one to tune into, ask Tyler your questions. Yeah. Today, we are super excited to have Haley Fox from EOS here to talk to us about design for additive manufacturing basics. In addition, I got confirmation this morning that you guys should have received access to EOS's Academy. Look at your email for a notice there and let me know if you didn't receive that. And between Haley and some others and myself, we can work that out if you didn't receive it. That's about it. So I'll turn it over to Haley, and I'm sure she's got some fantastic content for it. As per normal, we'll stop the recording at the end of Haley's content. We'll open it up for question and answer.
Okay, yeah, sounds great. Especially since it's a little bit of a smaller group. If you guys have questions, like during that you just want to pop in the chat, like while you think of them, that's fine. And then we can just kind of, yeah, answer them towards the end. So let me make this bigger so everybody can see that. So yeah, let's start with some design for additive manufacturing basics. So yeah, I'm sure you guys have heard the term, but I'm probably going to refer it to this as DFAM throughout, but you know, just in case, so you know what I'm talking about if I reference that. And just a little bit about me before I start. So I started at EOS as a co-op student and worked in the metals group. So that's how I got some experience there. And so now I'm full-time working in the polymer applications group. So I've had a little bit of experience with both, and both have been able to, in both experiences, I've been able to try different parts and learn about kind of like the design aspects for the different technologies. So before I get into it and talk about a lot of the almost constraints that we have with metal and polymer DFAM, I want to just talk about, you know, very fundamentals of DFAM before we get into it. So let me click through this. So what is DFAM specifically? So from traditional manufacturing, where we're taking maybe a large block of steel or whatever metal it is, and we're trying to chip away at it to produce a design that meets the functions that we want it to have. And so in that type of process, every sort of, you know, hole that we're drilling in the material or like face that we're milling, that's going to be an added step and an added cost. And so on the flip side of that, with additive manufacturing, we don't have to consider those types of costs and just all of those different steps. We can put material only where material needs to be to create the function for that specific part. So I have like 4 basic DFAM principles that I'm going to go over. And the first one is function-oriented to design. So when I'm thinking of a part, and I'm not thinking about any constraints, whether that's the type of printer that I'm printing it on, the type of material that I'm using, I'm not thinking about any of that right now. I'm just starting with the theory of putting material where material needs to be. So like for this application, we have maybe just a block, some kind of cooling channels going through it. And to design this in some sort of additive process, we might only, you know, put material around this hole in the back, only material around where the cooling channel is going to be. And we're not really thinking yet even about, you know, how we would print this in a printer. So I think as you go about your designs, and it sounds like you maybe have already started making those designs, but thinking about, where really the function is happening, whether that's a cooling channel like in this example, or a gripper or a hinge, just trying to figure out exactly what you need in order to make your part successful. And so this next one is material minimalism, and these kind of go on hand in hand, number 1 and 2. So when you're designing with function-oriented design, material minimalism will kind of follow that. But some designers kind of think differently. So maybe when you're thinking of the design, you might end up with something on the left still, because it's kind of function oriented, right? So you've got a large hole going through the center, and some other fixture holes. I'm not really sure what this end piece is supposed to do, but it looks like your design looks like everything serves a function here, but we still have a lot of material surrounding that. So we're going to take a lot of that out. You see in this example, they even punched a hole like through here, and really tried to make all of those thicknesses even, which is great. Next up, we have force flow design. And so this can be kind of a little bit more of a complicated topic. It also goes hand in hand with number 1 and number 2. But we are designing using the term topology optimization. And so this is a topology optimization is a tool based on an FEA analysis, where there's only material needed where there's going to be a force happening within that part. They also compare it to kind of like fluids, but I like to compare it to nature. You'll see a lot of people that study DFAM compare a lot of things to nature. So on the right here, kind of like a bee's wing. And so you can see that all of these lines and material, I guess, in that wing is needed to perform the function of the wing. And there's other examples. I'm sure if you were to Google, you'd find some other examples of how nature relates to organic designs and DFAM in general. It's really helpful to kind of understand that as well. And then the last thing, or the next slide there, soft edges and corners. So if you went to the previous or maybe it was the first one, first webinar with Gary, he said fillets are free, and that is totally true. So not only do fillets help with limiting some of the material in the design, but it also makes it look sleeker and an overall better design throughout. So that was quick on the fundamentals. Now I'm going to speak specifically on the metal side, and then I'll end with the polymer side. So now we have our thinking of the design. We have material only where material needs to be, and now we do have to start to constrain that. So I'm not exactly sure. Maybe if you guys have seen our printers and how they work, but just in case you didn't, I did include like a video of our metal powder bed process and our polymer powder bed process. So to start with the metal, we can see that we have a build plate, and right now we're building some tensile bars. They're just circular. And so this video shows spreading the powder over and then hitting the parts with a laser. Sometimes it does help to see a video of the process as you go about the certain design constraints. So if you're able to tell, we are building off of a build plate in metals. And because of that, we do need to support our parts similar to if we were printing with like an FDM or extrusion-based type printer. And so I do have some other pictures here. So we are printing with aluminum, so that's something to consider. We do have all of our data sheets on our EOS website if you don't have those yet. Like I said, we're printing with support structures, and so that's why it is pretty helpful to have an orientation in mind as you're designing, so that you know where those support structures are going to be. And then we're removing material where we can, especially because of the support structure. So if there is a large amount of material there, as you can see on this bottom left image, the part is actually lifting up on the sides where the supports are. or like where the connection to the support is. And that's because of all the internal stress. So the more material you remove from these areas, or thinking of the design or thinking of a different type of orientation, will avoid those structures from lifting off the supports. So you might print this in standing up, and you might have different design considerations if you choose to do that. And then I also have this picture on the right, just kind of showing how we went from the left image and to the right image, where we did have an orientation in mind, where all of these metal struts are kind of growing upwards, if you will. And so I would say this is a pretty good design for metal printing. However, because we were thinking of the previous fundamentals, there might be even some improvements in this design. So we might even put holes on the bottom where this like flat plate is, because we might be worried that that larger section could lift off of the supports, and yeah, just lose some more material if possible. All right, so just some more design guidelines. So usually holes are quite an issue when it comes to not only metal powder bed fusion, but also polymers. So you can see here that sometimes in this top right image, you can get away with holes being printed, I guess in an XY plane, or yeah, like kind of horizontal, if you will, printed through. And so you can, at some small hole size, you can get away with no supports inside, but you will always have this kind of like divot on the top. And so to avoid that, you might print a hole on this bottom right area. So instead of a completely round hole, if you could make it more of a teardrop shape, you would be able to avoid this top image with that little divot, or avoid the need for support at all, which is great. And the similar example with this stair step effect. So maybe you don't need a stair step at all. Maybe you can make it into more of a smooth, organic, like growing from the area. The next we have angles. So each material is going to have a different type of angle in which it doesn't need to be supported. So for aluminum, it's about 40 degrees from the XY plane. And so you can see this little picture here showing that we needed supports at all of these intervals on the under 40 degrees. This kind of looks like a 45 degree, but about the same. And then yeah, so the only other thing to note here is that maybe at like a 50 degrees or 60 degrees, you can get away with no supports. The only thing is you probably will have a rougher surface on that down skin, what we call it, down skin or downside surface. So yeah, if you can avoid some pretty shallow angles, that's always best. But if you can definitely avoid under a 40-45 degree angle, then you can get away with supports. Right. So, and then wall thickness, I did have this on a different slide. This is just to kind of illustrate further that different materials have different constraints on wall thicknesses. But in general, for most metals, you want to be larger than a 0.4 millimeter thickness. So you can see like this material at that thickness fared very well. But this material looks like maybe an Inconel did not fare well at these lower wall thicknesses. So I would recommend 0.4 or above. I'm sure with like the strength that you guys will need for your designs, you might be above that anyways. But just to consider, just in case you wanted to put like some sort of lattice in your part, and we can look at some lattices later on, especially when we talk about polymers. And then just some other examples. Oh, I guess I had that picture on twice on the right, but yeah, some other ways, like instead of putting supports over into this kind of like stair stepping on the top, maybe you can make them more look like grates so that you don't need any support in those areas. And then the top right is just kind of like an interesting picture. I guess I cut off my words there, but so this is something you guys won't have to support your builds, but this was an interesting case study that we did at EOS where instead of printing supports that adhered to the part and then afterwards they had to be taken off with pliers, they printed a little cup and then put the cup around the part. So, and there was just a small gap between the two that you could actually just pull the part right out of the cup, and you didn't even need really any support at all, or any more post-processing efforts on that. So just kind of an interesting case study, just to kind of, I guess, help you guys as you're, thinking about designs and creative ways to make your parts. And I think that might be, I have one more slide on metals, and this is related to aspect ratio. So our aspect ratio is basically how tall can you build a part on its own and how thick does it need to be before the recoder might make contact with that part and knock it over. And so we usually say an 8-to-1 ratio. So that means if you have a 8mm tall pin, that it would need to be at least 1mm for it not to have any like heavy contact with the recoder. Now, if you do, you're very welcome to put like latticing and different types of structures in your design. It's definitely encouraged because we do have different blade types of our recoder that recoat a soft layer of powder. They use like a brush instead of a steel blade. So this isn't to discourage you from doing these kind of like intricate small lines, but just so you know that it's also sometimes a design consideration. And that's it for metals. So now we're going into polymers. So here is just a quick polymer related video. It looks basically the same as metals, and it's kind of loud, so sorry about that if you can hear the sound. But essentially, it's the same process as metals. We're still recoating a small layer of powder over a build volume, and then a laser is sintering the rest of the powder. Key difference here, though, is no supports. So this is really exciting, and one of my favorite things from switching to metals to polymers is the need for no supports. However, even though no supports are needed, orientation can still be important because of what we call a stepping effect, and that's this bottom right picture here. So the stepping effect is basically at pretty low angles, maybe 10 to 30 degrees off the XY plane. You can see on the bottom surface and on the top surface some pretty distinct layer lines. We're also printing at larger layers in polymers compared to metals. And so this is another reason why that stepping or layer line effect is so much stronger. So you can see on, sorry about that. So you can see on the very right side, we have a part printed flat, and then one bar left to that was printed at like 10 degrees. So we can definitely see that stepping effect. And then as you go from higher degrees, 45 degrees is always pretty much considered good, and won't have super high stepping effects. This might not be, something that you definitely need to consider in your designs. This is more of an aesthetic thing, surface finish related thing. But a lot of, what I do in my job when I'm working with customers is I try to avoid any harsh stepping angles. And then, these parts are going to be printed in a nylon 12, PA 2200 in particular, and this data sheet is also on the EOS website for you to be able to find. And then holes, so like I mentioned with metals, holes, if they're not going straight up and down in the Z direction, they might look a little squished. Because of an extra heat and the laser going through and hitting in those areas, they'll kind of compress instead of be perfectly round. And so if you are choosing to go the polymer route, it's probably best to keep most of your holes in the going vertically up in the Z direction. Not a requirement. It's just something that if you do have like something mating together, you would want to make sure that's perfectly round, and so you want to print it in Z. And then from the polymer side, so probably the most difficult thing on the metal side is support removal. And then similarly, so that's the post-processing side. Similarly, in polymers, the post-processing side is also difficult. And that's because the powder kind of wants to stick more on internal channels. And so sometimes powder removal and getting everything out can be a challenge. We like to use a 1:8 ratio, similarly to the 1:8 ratio that I just showed you before for metals. This is how long you would make a channel based on how large that hole is. And this is for getting powder out. So if you made if you have a 1 millimeter hole diameter, you probably wouldn't want to make a channel that's longer than 8 millimeters, because then powder removal is going to be very difficult. And then also minimum wall thickness of 0.8 millimeters, which I have some more right here. This is a little bit more into the wall thicknesses. So for polymers, there's a bigger difference on minimum wall thickness, whether you're printing in X and Y versus whether you're printing in Z. So for XY, in the machine that we're going to run these parts in, it's about 0.7 millimeters, and then in X and Y, and 0.4 millimeters in Z. So that's good to know, just in case you are, I keep mentioning latticing. I have some pictures of latticing at the end of my presentation. But if you are doing some smaller work there, it is nice to kind of know what orientation you might print this in. You don't have to fully understand the orientation and what's best, because we'll definitely help with that when we print it. But yeah, just good to know the differences between these two. And then for pins, the same. You probably could say 0.8 millimeters is probably just a universal pin diameter that you should stick to, that and above. Getting into hinges. So if there are aspects of your design that might benefit from this, I really like talking about hinges because there's a lot of interesting design changes you can make in Additive. So there are some, different gaps that you want to consider if that hinge area is being printed in X and Y versus Z. But an interesting picture here is actually how heat really makes a big difference when we're talking about hinges. So on the left, on this bottom picture here, we see that just filling in with just a random fill is bad. And that's because if that gap is not big enough, all of that excess heat will center around those parts and kind of glue it in place and not let the hinge work. So instead, if you can get rid of a lot of material, kind of like on the right side, you can get rid of that material, then your hinge has a better chance of working, especially with these tolerance or these values given, like 0.3 to 0.8 millimeters. Yeah, if you have more material out, less heat going into the part, the hinge will be a lot better, and then you'll also reduce the amount of material in your part as well, which is always good. All right, and then so I guess on the end, just 0.5 millimeters is probably a good starting point if you do decide to use hinges in your design. All right, I think I've just got a few more slides. I know we're getting to almost half an hour. So we're talking about here just powder removal again. So wanting to make sure that you are able to remove all the powder in the parts. So definitely make sure not to have any, if you hollowed out a section of your part, make sure there are different holes in that to be able to remove that powder out of. They're showing some good and bad examples of, this coil right here would be virtually impossible to get all that powder out. But if you had an area where you are a little bit worried of getting powder out, you might consider some sort of chain going through it. So I have had parts before where I have had a longer channel than that 1:8 ratio, and I print just a small chain throughout so that I can pull that chain out once it's done printing, and then it's easier to blast, do a different media blast to get the rest of the powder out of that inside. And yeah, that's the rest on that slide, I think. Yeah, that's basically it. So this is my last slide. This is just kind of like a end inspiration slide. I've got, I know I mentioned lattices a few times, so this bottom picture is just showing you some different lattices. Usually we like to use lattices for elastomer materials, parts that squish, but lattices can also be used for a harder plastic material, especially if you're trying to lightweight your design. Just a few different interesting applications. This bottom right, where they took this chair and they did sort of like a topology optimized chair to find exactly where the material was needed for the different stresses that the chair would see. And then this left image is a really cool project that they got to work on the metal side. They worked with this group called Hyperganic, where they have this software that is integrated with an AI, and they basically plugged in all the parameters that said, we're printing in this this type of material. We want to build a rocket engine with these certain parameters, and the AI was able to spit out this design for additive. And I love how it still has the traits of designing for metal additive. So you can see there's no really any 45 overhanging angles. Everything kind of grows upwards, and then it's still a beautiful concept idea of what a rocket engine could be like printed in additive. So I guess my final words would just be to think like an AI, I guess, does. You know, think how how you could design a part like this where everything is growing up and everything is purposeful for that specific design. So yeah, that is pretty much the end of my presentation. I'd love to hear if you guys have any questions that I can answer, and I can also reference back any of the slides that I've had. So thank you very much.
I had two thoughts, Haley, and a question.
Sure.
So the one thought I will add is Haley talked a lot about post-processing of parts after you get it off. And that is one of the largest cost additions of additive parts. And so when we talk about DFAM and when we talk about, these drone chassis and stuff, we want to see you take into consideration not just can it be printed, but can it be printed so that it doesn't need as much post-processing? Because all of that post-processing, that's hand touch time. And a technician or an engineer who's doing that, that's very, very expensive to add to a manufacturing process, as well as it's just another opportunity for something to break. If you're taking a file to a support structure, or you're taking tools to try and get powder out of an SOS part, that's just more and more opportunities for that part to break. And then you have to start a whole nother build again. The other thing that I loved about Haley's presentation is the example of that hinge, right? Things we get in our minds, the idea is that things have to look a certain way, right? We've all seen door hinges, we've seen things like that. And so we're used to that cylinder in a cylinder design. But I'd encourage you as you're looking at these drone chassis, think about every decision you're making and about why you're making that decision. Are you making that decision because that's the way it's been done before? Or are you really designing with the end use in mind? And that lattice hinge is a fantastic example of that, where you don't need that whole cylinder for a hinge to work. And you're getting away with less material, you're getting away with less risk by reducing that. Lastly, the question for Haley. So I'm sure that one of the questions that is going through the students' minds is, on a judging scale of things, what kind of things for a drone chassis would judges potentially be looking at for DFAM?
Yeah, so yes, and remind me too, so it's supposed to serve a function of like medical supplies, right? And
It's
transporting
going to
that.
be delivering medical supplies, yeah.
Yeah. Yeah, so I would kind of think about, is your design meeting that function? So like, is it like in how it's carrying the design, would it kind of like those fundamentals that I talked about at the beginning? So is there just material where material needs to be? Does it feel like it's been thought out? And yeah, I honestly I don't know if I have a lot of answer for this question. I like to see students, because I've done some similar design competitions with just like sort of giveaway parts, and I really like to see the design, really consider all the steps of the process. So I'm glad that you said a lot on the post-processing side, because I think that's the biggest thing that most of our customers honestly just forget about. And so if you can design with post-processing in mind and material where material needs to be for that function, yeah, that's what I would look for specifically. I don't know if that relates specifically to your guys' project, but that's in general what we would look for in DFAM.
That's great. Okay, I'm gonna go ahead and stop the recording, and then I'll turn on you guys' microphone ability, and we'll let Haley answer your questions. Go ahead.